ask their questions in a private discussion with the speaker. If you're a graduate student on YouTube, you can participate in these 20-minute discussions before and after the colloquium by registering to the physics discussions at ICTP-SAIFR's website. So our dear guest today is Professor Jolien Creighton. Professor Creighton received his PhD from the University of Waterloo in 1996. Then he spent 3 years as a postdoctoral scholar at Caltech. In 1999, he went to the University of Wisconsin-Milwaukee to work as a research associate. In 2002, Professor Creighton joined the faculty, becoming an associate professor in 2007, and holds the rank of professor since 2013. Creighton has been chair of the LIGO Scientific Collaboration, LSC, Internal Review Committee during 5 years, librarian of the LIGO LSC algorithm library since the year 2000, and has received 6 awards from the National Science Foundation. He's here to talk about 5 years of gravitational wave astronomy, and you can, I think you can share your screen.
Yep, let's see.
Okay. Good.
Okay.
As the title of the presentation advertised, so please welcome. The stage is yours, Professor.
Okay, thank you. This title is slightly out of date. It's more like 5.6 years of gravitational wave astronomy since the very first detection. But our first publication was about 5 years of detected gravitational wave was about 5 years ago. So I think I'm going to stick with the title for now. All right. So what I want to do in this talk is first, because not everybody is a gravitational wave scientist, I want to give you some description about what gravitational waves are, how we detect them, what LIGO and the other detectors that we use are. And then I'm going to do a very rapid run through some of what I think are the more interesting detections that we've made, and what kinds of insights that we've had, both in terms of fundamental physics, in terms of astrophysics, and in terms of cosmology, coming from some of these recent detections over the past 5 years. So let me just start off by saying what a gravitational wave is. So gravitational wave is it's predicted by general relativity. General relativity is a theory of gravity that describes it as the geometry of space-time. So a gravitational wave is like an electromagnetic wave. It's something that propagates through space-time, but it is also of space-time. And so the effect of a gravitational wave is simply to change the geometry of objects. So if I have a picture on a wall that has a certain proportion, like what's shown here. Oops, I need to let me turn on a laser pointer. Then as a gravitational wave passes through the wall, as time goes on, that figure will be distorted. So circles will become ellipses, squares will become rectangles as the crest of the wave passes through. And then as the trough of the wave goes through, this picture of a person will become shorter and wider. So the person might become taller and thinner, and then shorter and wider, just as this gravitational wave passes through. And there are waves passing through us, constantly. So in fact, we are continually being distorted in this way. And the reason that we don't typically notice this fact is because the amount of distortion, which we call strain, which in this example might be how much taller this person gets relative to their height, so fractional change in their height, For typical gravitational waves that we'll be talking about, that fractional change in height is on the order of 10 to the minus 21. And to make that in some sort of astrophysical context, that means that if the distance that we're measuring is the distance to the nearest star, Alpha Centauri, then we're looking for a fractional change in that distance that is about the width of a hair. So it is totally unperceivable unless you build a $1 billion detector on Earth. In general relativity, there are two polarizations of gravitational waves that are predicted. So just like there are two electromagnetic polarizations, the Einstein field equation emits two different gravitational wave polarizations. And these are called plus and cross because of the shape of their geometric distortions. A plus is what I just depicted before, makes you taller and thinner or shorter and wider. So that's the plus polarization. And then the cross polarization is basically just a 45-degree rotation of that. So those are the two different polarizations. They're both transverse, I should mention too. So the gravitational wave here is traveling into your screen. So the method that we use to detect these is basically 19th century method of trying to detect the ether with a interferometer. We now use lasers these days instead of white light. But the basic idea is the same as the Michelson-Morley experiment, where you're looking for a distortion of your interferometer that makes one arm slightly longer, the other arm slightly less long, and then instead of perfect interference in the antisymmetric port, you get a little bit of light leaking out. So here the arms are arranged to be equally length. The beam splitter recombines with constructive interference that way and destructive interference that way. But that's ruined when the lengths of the arm are changed. All right, I mentioned that the amount of distortion is for a given amount of strain is proportional to the length of the arms. So the detectors we use have very long arms. So these are the two LIGO detectors, one in Washington State in the United States. These arms are 4 kilometers long. A second one is in Livingston, Louisiana, so in Louisiana in the United States. And it also has 4 kilometer long arms. And these two are the LIGO detectors, and they've been operating since the early 2000s, but in a more advanced interferometer configuration, they've been operating since 2015, approximately a day before the first detection. In addition, there's 2 other detectors that are now operating, one in Japan, which is underground, called Kagra, and one in Italy near Pisa, and that's called Virgo. So the full network of kilometer scale gravitational waves now numbers 4. All right, so let me briefly describe the kinds of sources that we're looking for. So in electromagnetic radiation, the dominant form of radiation is dipole radiation. You don't have any monopole radiation because charge is conserved, and so you can't make electrons appear and disappear, but you can have a time-changing dipole. In gravitation, you can't have a time-changing mass dipole because momentum is conserved. So the dominant source of gravitational radiation turns out to be quadrupole radiation. And so a prototypical quadrupole system might be two masses that are orbiting each other. And in fact, this is the kind of system that we've detected. So we normally detect two black holes in orbit around each other, which makes a time-changing quadrupole. The quadrupole formula was written down by Einstein shortly after the Einstein field equations. So he predicted the amount of quadrupolar radiation a system like this, an orbiting binary, would produce. The quadrupole formula predicts a particular emission pattern of radiation that's given by this figure, this envelope. And the way to read this is that if you're sitting above the system, like around here, you've got maximum amount of radiation. You get half the amplitude of radiation if you're sort of on the equator over here, but that can dip to nodes sort of in between these two objects. So this is the typical emission antenna pattern for the plus polarization. The cross polarization looks somewhat different. Again, you get maximum amount of cross polarization sort of above and below the system. So if you're sitting above or below the system, you actually have circular polarization. So you got equal amounts of cross polarization and plus polarization. But on the cross polarization, if you're at the equator of the system, that you actually get no radiation in that polarization. What happens with our binary systems, say a binary black hole system, is that as it orbits, it radiates gravitational waves, and that causes it to lose energy. So as it loses energy, the orbit shrinks, and the two components start orbiting faster, so with a higher frequency, and they also are producing gravitational waves with a higher amplitude. So the gravitational field forces are getting stronger, and gravitational radiation and the speeds are getting faster, and so the gravitational waves get stronger. So we start with gravitational waves that are sinusoids. They come out at twice the orbital frequency, and then the frequency increases with time, and the amplitude also increases with time. And that drives these two systems together. If they're black holes, they'll coalesce to form a single. The cross section of the black hole at the end is a single sphere. So here is what we would expect to see in terms of the strain in one of our instruments. It's a sinusoid that comes out at twice the orbital frequency, which increases in frequency and amplitude as time goes on. It reaches a peak at about the same time as the cross-section of the black hole is simply connected, and then it dies off exponentially at the end in a way that's characteristic of black holes. And that's actually the signal that we saw shortly after starting our first observing run of the advanced detectors on September 15th, 2015. And here is a depiction of the data that we saw in the LIGO detectors. On the bottom here, you see traces of the strain that was measured in the instruments for about 0.2 seconds. And you can see the waveform is increasing in frequency and amplitude and then dying off as predicted by general relativity. In the background, there's another depiction of this, which is sort of useful, where you plot the frequency versus time, and then this swoop here shows how it starts at low frequency, ramps up to higher frequency, and then the brightness increases, which is the power in the strain signal. And we saw that simultaneously in Hanford and Livingston with very short time delay due to light propagation between the two systems. Okay, that was the very first observation of gravitational waves, and it was a confirmation of that Einstein's theory of gravity, in fact, which predicted gravitational waves. In fact, gravitational waves do exist and are directly observable. So that was a major sort of prediction of general relativity that was verified by this observation. Another one was this was a direct observation of a black hole from the gravitational waves that are produced by it settling down. So that was also the first time that we had seen black hole and gravitational waves. Since then, in the first 3 observing runs, these represent all of the different signals that we've seen. And the way to interpret this chart is that the y-axis is mass, and the x-axis is just that doesn't have any meaning. It's just to separate the events. And you see what happens here is these are 2 black holes. These are the initial masses of the separate components, and then they're joined by a line to represent the joining of those 2 masses to form the to form this black hole here. Pointers disappeared. And so each one of these triples of points represents one gravitational wave event. And what's shown here is a total of 50 different events. So let me talk about the black hole binaries first, and I'm just going to highlight a few of them. So this event here was the first one that we saw. That's the one I've already talked about, 1509-14, because it happened in 2015 on September 14th. So I think I got my slide wrong before. It's 1509-14. So let me talk about a different event that happened a couple of years later, during our second science run, which was GW 1708-14, which is this one over here, which was interesting because it was the first gravitational wave that was observed with 3 different detectors. So by this point in time, the Virgo detector, the one in Pisa, had joined our network. And the importance of that in gravitational wave science is that our detectors don't clearly respond to some detect. They do depend on which direction the gravitational wave is coming from, but not like a telescope. They don't pinpoint things in the sky on their own. Instead, what we do to locate something in the sky is we figure out the time delay of an event between 2 detectors, which will constrain the possible position. So if we've got 2 LIGO detectors, then for a fixed time delay, that means that the system must have come from some annulus in the sky, a locus of points that are equal time for the 2 detectors, or a constant time difference between the 2 detectors. So this might be the constant time ring for Hanford and Livingston. But then there'll be 2 other rings if we have a Virgo detector, one for Livingston and Virgo, and the other for Hanford and Virgo. And these rings, when you have 3 detectors, they will intersect in only 2 places. And that's how we could localize a signal in the sky. And in fact, we do get a little information from the amplitude response of the detectors. And so this sort of banana shape is actually what we would get if we just used the LIGO detectors to localize the source from the time delays and the amplitudes. but including the Virgo detector, we were able to localize this particular event to a rather small portion of the sky. Now, this is going to be very useful when we talk about multi-messenger astronomy, where we want to now follow up with the telescope. But for black holes, we don't normally expect there to be any associated electromagnetic radiation. So what's cool about this event is that localization did allow us to test one of the predictions of general relativity, which is the fact that there are only two polarization states. So these are the two states, the plus and the cross, that I described before, that are predicted by general relativity. But in general, a metrical theory of gravity could allow up to 6. The Einstein field equation means that these 4 are ruled out. This polarization state is a transverse state that, instead of stretching along one axis and squeezing it along another, it is an overall dilation or contraction of an object. The person gets either bigger in all directions or smaller in all directions, or in all transverse directions. There are also possible longitudinal waves. So here the wave would be traveling towards the right, and then the distortions have some sort of longitudinal and transverse components. So these are 2 vector modes. And then this is also a scalar mode where it's purely longitudinal. Well, the detectors do have some directional sensitivity. So these are the directional sensitivities of the detectors to plus polarizations and cross polarizations. So these are the 2 arms of a detector. And since we know where in the sky this thing is from the time localizations, we can make a prediction about how the plus and cross signal should be, and contrast them to what the antenna patterns we would have for vector. So the response patterns for vector or scalar arrays. And so since we knew which direction things came from, and we knew the amplitudes, so we saw them in the 3 different detectors, we were able to basically rule out pure vector radiation compared to pure tensor radiation at 200 to 1 odds, and pure scalar radiation versus pure tensor radiation at like a 1000 to 1 odds. So this allowed us to show that this prediction of general relativity, that only 2 polarization states, what is in fact most likely the case. Okay, so here's the next detection I want to focus on, and this was from the 3rd observing run. So this is GW 1904-12, so 2019-04-12. So this is shortly after the 3rd observing run began. And what's interesting about this event is it was the first event that we had with a rather large ratio of masses between the primary black hole and the secondary black hole, so quite distinct masses. So this plot shows a probability distribution of the mass ratio. There's 2 curves because it's a little difficult to model high mass ratio systems. So different models might predict different mass ratios. So this is a secondary mass, so smaller mass over the larger mass. But you can see that it's the mass ratio is certainly bigger than 2 to 1, and maybe even as large as 5 to 1 between these 2 systems. Now, this has an important physical effect that we can test, because I said that earlier that Einstein wrote down a formula to describe quadrupole radiation in general relativity. But just like in electromagnetism, you have dipole radiation, quadrupole radiation, octupole radiation. General relativity was expected to go beyond quadrupole radiation. and predict octopole and hexadecapole and these higher modes of radiation. We have never actually seen such modes of radiation before, for a couple of reasons, one of which is that they are suppressed by factors of V over C, just like they are in electromagnetic radiation. And so unless we have things moving very close to the speed of light, these are significantly suppressed. But they are also, many of the modes that we would hope to detect are suppressed when the two components are equal mass. So the amount of radiation in the octopole radiation mode that I've shown here is proportional to the difference in the masses. So this was the first system in which we were able to actually detect octopole gravitational radiation. So this is another test of general relativity. And so basically what happens is I said that this radiation comes off at twice the orbital frequency. Octopole radiation can come off at, well, it can come off at 1, 2, or 3 times the orbital frequency. So the way we detect the octopole radiation is this is the swoop that I showed before, frequency versus time. What we can do, so this would be an m equals 2 mode of radiation, the quadrupole mode. We can sort of figure out what the track is where we would expect octopole radiation at the m equals 3 type to be, and sort of do do some data analysis to try and pick out the swoop that's there. It's not visible in this, but if you do the detailed match filtering, you can actually pick out that octopole radiation. And a model selection of gravity without octopole radiation versus gravity with octopole radiation is favored about 1,000 to 1 based on this observation. So that was the first time. So that's another test of general relativity that we were able to do just recently. I want to talk a little bit about astrophysics. In the spectrum of compact binary masses, these things down here, these orange things, are neutron stars. So these are neutron star binaries. And these blue things are all black holes. In the spectrum of compact binaries, ranging from neutron stars to black holes, we observe in our galaxy that there is a band where between the heaviest neutron star that's been observed and the lightest black hole that's been observed, that is vacant. So there's an observed mass gap between neutron stars and black holes based on galactic observations. There is another mass gap that's predicted from basically stellar models and supernova physics in the upper mass gap, it's called, at high masses where we don't expect to be able to form black holes. And you can see from all of the observations that we have so far, well, we do see some black holes in this region, in this mass gap here, but they are actually just the products of two black holes that were below the mass gap. So, the stars would evolve to produce these black holes down here, and then they merge to produce something that's in this mass gap. So none of these are surprising at all to find, except for this one, which was something that we saw in the third observing run, 1905-21. And here we see that the progenitor black holes, one or maybe both of them, are actually sitting in this theoretical mass gap here. And here's a plot of the more massive probability distribution that we get from parameter estimation. and the secondary mass. And you can see that this is somewhere around 80 or 100 solar masses, the primary. And here's that mass gap again with the primary mass in a block. And what this plot is showing, I'll just run through it briefly, is predicted black hole masses produced by initial stars. So on the x-axis, we have initial star mass, and then on the y-axis, we have the mass that we would expect that star, mass of the black hole we would expect that star to produce at the end of its life. And the different curves would be for different metallicity stars. So how pure the hydrogen is in the star. These two curves, these solid curves, are early universe stars that are very pure in hydrogen. And then these other curves are for more recent stars that have other chemicals in the gas of the star. But you see that no matter what, there's none of these stars, none of these initial stars are expected to produce black holes in this gap. These light things you'd think would continue across there, but there's an instability in the star that occurs in this mass region that prevents this curve from being continuous through that mass gap. So once the star gets heavy enough, it just directly collapses into a black hole. So that leaves, that's a bit of a conundrum still, how this black hole system that we observed formed. It doesn't seem that it should have formed from regular stellar evolution. So there's several different scenarios that we've considered. Maybe there's hierarchical black hole mergers. So maybe if I go back to this plot here, maybe we had one system that produced a black hole in the mass gap, and another system that produced a black hole in the mass gap. And if they were in some cluster, then those two things were the two black holes that we observed. So maybe there's two black holes that merge and then form a second generation black hole which merges. Or perhaps this wasn't regular stellar evolution, and that two regular stars merged and somehow caused atypical stellar merger, stellar evolution that produced a black hole where it wasn't supposed to be. Or another thing that is possible is that these black holes actually, this black hole binary actually formed in a accretion disk of an active galactic nucleus, so with a supermassive black hole in an accretion disk, and then siphoned off some of the gas in the accretion disk and grew into that mass range. And then there are some more exotic scenarios. Maybe we got the waveform wrong because it's in fact an eccentric binary, and we modeled it as a circular binary. And so maybe we estimated the masses of those black holes wrong. Or maybe we estimated the masses of the black holes wrong because it was a magnified black hole from strong gravitational lensing, which made us think that it was closer than it was, which so we didn't properly account for the gravitational redshift or the cosmological redshift, which would have affected our inferred masses. Or maybe these black holes were formed in the early universe, or which are called primordial black holes. So there's lots of different kinds of questions that this kind of system raises, and we're looking forward to seeing in the future more such systems so we can start trying to rule out some of these scenarios. Okay, the next system I'm going to talk about starts to probe into this lower mass gap. So this is GW 190814. So seen in August 14th of 2019. And it's interesting because it's also got a huge mass ratio. And we also saw higher modes of octopole radiation from this as well. But this lower mass thing is kind of sitting at one of the boundaries of this lower mass gap. So in a place where we haven't previously seen any sorts of black holes or neutron stars. So here's a mass-mass plot again. So here's the secondary mass, which is now the interesting one, sort of between 2.5 and 2.7 solar masses. And this is actually just at the region where we don't know whether that object would be, in fact, a black hole or a neutron star. It depends. We don't know exactly what neutron stars are made out of. We don't know the equation of state of the matter in the neutron star. And depending on what it is, that object could be either a black hole or a neutron star. But no matter what, it's either the most massive neutron star that we've ever observed or the lowest mass black hole that we've ever observed. So it's interesting either way. Based on what we know about neutron stars, we think it was more likely a black hole. Okay, so now I want to switch gears and talk about some of the binary neutron stars systems that we've observed. And the first one, which is probably the most famous, is GW 170817. So this was an event that we saw in the second observing run. And this is a collision between two rather run-of-the-mill, ordinary, close to 1.4 solar mass neutron stars. It was interesting because it was the very first binary neutron star system that we observed with LIGO. The previous events had all been binary black holes. But it was also incredible because it was the first multi-messenger astronomy system that we found with gravitational waves. And what I mean by that is you get both electromagnetic waves and gravitational waves. So this plot here shows the swoop of our binary neutron star sweeping up in frequency with time. And on top of this is gamma ray counts observed in the Fermi gamma ray satellite. And approximately 1.7 seconds after the merger of our neutron stars, we saw a gamma ray burst. Again, we had 3 detectors operating. This was shortly after that triple detector binary black hole. It was like 3 days later. And so we were again able to draw constant time delay rings. Now this really thin ring here is Hanford and Livingston. And so we were able with that to localize this system in the sky. And this time it was important because that allowed the optical astronomers within a day to find the optical counterpart in a nearby galaxy. And so this is the new kilonova, it's called, created by this by the debris from the binary neutron star. So this is shining in radioactive decay. And as time went on, this system dimmed and faded and turned red. Now that dimming and fading and turning red gave us what allowed us to answer a question that's been lingering around in astronomy for a while, which is how do you form a bunch of these elements, all these elements that have lots of yellow on them? It was a bit of a mystery how to form them. They are not elements that are formed normally in supernovae. Elements that are formed in supernovae are these more blue colored elements. And it turns out that dimming and fading red is modeled by the radioactive decay of a lot of these higher atomic number elements. So this allowed us to directly observe that a lot of these lanthanides and actinides are primarily produced in binary neutron star collisions rather than in supernovae. So, for example, gold, like in a Nobel Prize, most of that gold comes from two neutron stars that collided a long time ago in our galaxy. Another important bit of fundamental physics that we learned from this event was could be deduced from just the fact that these gamma rays came to us within a couple seconds of the gravitational waves. And that allowed us a way to directly measure the speed of gravitational waves. They are equal to the speed of light. And the light was only 2 light seconds behind the gravitational waves. So it's plus or minus 2 light seconds in the amount of time it took to get here. From the distance, it was 100 million years. So 2 light seconds in 100 million years is the difference from the speed of light. So this is our measurement of the speed of gravitational waves to within, a micrometer per second. Before this event, we did not know what the speed of gravitational waves was. After this event, we knew it to within a micrometer per second. In terms of cosmology, this is interesting because it allows us to make a measurement of the Hubble constant. So for people, to remind people what the Hubble constant is, this is Hubble's famous Hubble diagram. He plotted the recessional velocity, so the radial velocity of distant nebulae or galaxies, versus the distance to those galaxies measured from some period luminosity relationship for Cepheid variables. And you see all these different points are different Cepheid variables or variable stars, where you can measure the redshift from the recessional velocity from the redshift and the distance from the period luminosity relation. And you can draw a line through this, and the slope of this line is the Hubble constant, and it basically tells you how fast the universe is expanding at the present day. So it's about 500 kilometers per second per megaparsec, or that was the value of the Hubble constant at the time. It's now more refined measurements give it something closer to 70 kilometers per second per megaparsec. Well, the gravitational waves give us a direct measurement of the distance. In astronomy units, this was about 40 megaparsecs away. So this is our error bar in the distance. Since we saw the host galaxy, we can measure the redshift, and so the radial velocity of that galaxy, and that gives us this error bar. So here's our one point on our gravitational wave Hubble diagram. And what we do is we draw a straight line through that point from the origin, and that slope is our measurement of the Hubble constant. And that's given in this blue line with the error bars. And on top of this, what I've plotted are the 2 best measurements of the Hubble constant that we have so far from supernovae, which is this yellow line, and from the Planck satellite looking at the cosmic microwave background, which is this purple line. And you see that we, with just a single data point, have measured the Hubble constant completely consistently with both of these measurements. What's a little curious is that these 2 measurements, which are very accurate, don't agree with each other. So there's some tension in the value of the Hubble constant. so we're kind of hoping that with enough similar systems with the gravitational waves, instead of having just one point in our diagram and fitting a line through one point, we'll eventually be able to get many points and narrow this error bar down, and hopefully try and resolve the difference between supernova methods and cosmic microwave background methods for measuring the Hubble constant. Okay, the next thing that we learned from this binary neutron star event was something about the, I see there's something in the chat.
Oh yeah, so there's a question in the chat. Do you mind if I read? Or you?
Okay. While computing the speed of gravitational waves with respect to the speed of light, do you take into account any obscuration of the incoming gamma rays by the intervening medium and or massive objects in their path? No. And that gamma rays probably aren't greatly affected by obscuration, because they're pretty high energy, so they don't disperse as much as radio waves would in the intergalactic medium. But of course they do have to undergo the material. They have to plow through the material, any material that's at the source. But that any sort of obscuration would slow down the gamma rays, and they already arrived later than the gravitational waves. So that would just increase. So if there was any of that, then that's already accounted for in the 2 seconds delay time. So we don't think that there was a lot, but it certainly wasn't more than 1.7 seconds worth, because otherwise it would have arrived even later. In terms of any other massive objects in their path, that's an interesting question. We would actually expect gravitational waves and light to be affected equally by any sort of lensing or Shapiro delay or such things. So we would normally expect that both the gravitons and the photons to feel those effects similarly.
We have some questions from YouTube. Can I read them?
Oh, sure, yeah.
Okay, so Ed Wilson Hawk, he asks, what aspects were considered when in planning the observatory's locations?
All right. There's politics. So LIGO was a US-based thing. The locations within the US were probably somewhat influenced by politics. People wanted big science projects in their state. Obviously, you want it to be in some flat and reasonably remote region. We would have liked Louisiana to be a little bit more remote and a little bit less swampy, but that's where it ended up being. One thing that was done, though, was to try and make the L-shaped arms as aligned as possible, so that they would have very similar responses to gravitational waves.
We have another question from Sun Cloud. He said, wasn't this 2-second delay used in gravitational wave speed calculation?
Sorry, I missed.
Wasn't the 2-second delay used in the gravitational wave speed calculation? I didn't actually understand.
Yeah, maybe.
Can you be more specific? And I have a. Okay, he's talking.
I'm sorry if I'm interrupting your lecture a
No.
little bit. So you said that the 2-second delay is caused by whatever medium or maybe the cause of massive objects in the path of gamma rays is. So then there is that assumption that gravitational waves are at the same speed of light. So, I mean, you're saying you're using this delay. Weren't you using this delay to see how accurate the speed of gravitational waves is, or sort of the value or the error in it? So, if you are saying these gamma rays came later because of the medium, and but then saying gravitational waves are of the same speed as gamma rays, aren't we being a bit circular in using that to you know um, establish the speed of gravitational waves?
Yeah, I think that's a fair point. It is rather circular. I mean, if they were very different, we would have never expected to see a gamma ray burst associated with the gravitational wave. So it is a bit circular, and I think that the upshot is that you shouldn't read too much. You shouldn't read too much into the exact numbers on this plus or minus, because is it 2 seconds, or could it have been 4 seconds and then been a little bit slow, or been a little bit faster, and the gravitational waves caught up a little bit, or but you would have to very finely tune any difference to have this many digits of precision. So I would say that, yeah, you might call into question whether this should be 2 seconds or 10 seconds or plus or minus how much. It's probably due to a delay between the actual merger and when the gamma rays are produced, but there could be other mechanisms. So I wouldn't count on this very last digit to be a fully accurate estimate of the uncertainty. But it is like 1 part in 10 to the 14. So it's pretty close.
Thank you.
Okay, was there another question in chat, or should I continue?
No, you can continue.
Okay, thanks. Okay, so I just wanted to say a few things about the equation of state of neutron stars, and then probably this will be the last topic. I mentioned before that we don't really know what the structure of what the maximum mass of a neutron star. It's because the material that makes up the core of a neutron star is denser than nuclear matter, and there's just absolutely no way of creating such matter, at least at low temperatures, in terrestrial experiments. So really, the matter that makes up neutron stars only exists in neutron stars. So if we want to study cold matter at extreme densities, the only way we can do that is by observing neutron stars. And we don't know what that is, if it's hyperon material, if it's deconfined quarks or color superconductors, or all sorts of different kinds of strong force effects. There are different approximations of QCD that are used to try and model this matter, and they make different predictions about what the nature of the matter is at these densities. And these predictions are basically given by by curves that are called equation of state curves, which is basically describing the pressure as a function of the density or energy density here. And these are different nuclear physics models, and they predict different pressures as a function of density. Now, if we feed this curves of pressure versus density into the neutron star structure equation, so relativistic hydrostatic equations, we did get different predictions for what the radius of a star, of their neutron star, will be for a given mass. So for a 1.5 mass star, then this APR4 equation of state would predict a 11.5 kilometer radius neutron star. But one of these, this equation of state might predict a 13 kilometer star. So the size of the neutron star depends on the equation of state. And also these things turn over at the maximum mass of the neutron star. So these equations of state also predict different maximum masses. So by studying properties of neutron stars, like their maximum mass or their size at a given radius, we can start to basically invert these curves to get these curves, which tells us about nuclear physics. Well, in gravitational waves, what happens is that as their two neutron stars approach each other, as the orbit shrinks, they start to deform each other. Their tidal interaction causes a quadrupolar deformation. And then these two, this takes energy, so it takes energy out of the orbit, and it also radiates more because we've got two more quadrupoles that are swinging around. So what this does is it causes the in spiral to go faster, for it to sweep up in frequency faster, the more distortion there is. And for bigger neutron stars, there will be more distortion than for smaller neutron stars. And so we were able, with this observation, to also make a measurement of the mass and the radius of our two neutron stars. So this is the top curve is one neutron star, and the top and the bottom curve is the other neutron star. And this is a probability distribution in the mass radius space. And on this, I've superimposed several different equations of state, and you can see that some of them are flowing through our posterior, so they are consistent with our observations, but other equations of state have now been ruled out. They are inconsistent with our observed mass and radius of this neutron star system. So hopefully when we get a bunch more binary neutron stars, we'll be able to put smaller and smaller constraints on this curve and maybe figure out exactly which equation of state is describing our system. And I think I'm out of time, so I'm going to leave off the last topic and just finish with the last neutron star that we saw, and just finish with a summary of the kinds of things that we've been able to do in the past 5 years. There's the direct detection of gravitational waves, the detection of the post-quadrupole radiation, and confirmation of tensor polarization, speed of gravity, and the equation of state of dense matter. And there's also a lot of astronomy that we've managed to do. So I think I should stop here.
Okay, so thank you for the nice talk. Now we have some questions from YouTube. Edmilson Hawk is asking, how does it take to run? How does it take a run of the observatories? How much data does it take?
Oh, all right. That's an interesting question. So the gravitational wave channel, the strain that we observe, we sample at 16 kilohertz. So it's like an audio channel. It's kind of like just recording an audio channel for Zoom or something. So it's not a lot. But there are thousands and thousands and thousands of environmental channels and other interferometer channels and things that we record. So it's a large number of like hundreds of terabytes of data during an observing run, of which the channel that we mostly are interested in terms of the data analysis point of view is actually just about 16 kilohertz times a year or something.
So we have a question from Matheus. So how do you choose between different ways of modeling the black hole binaries? What is the rule to choose between them?
Between the what and modeling them?
Modeling the black hole binaries must be the model. How do you choose the model?
All right. Yeah. So there's different techniques for modeling them. There are point particle methods that are post-Keplerian. So you have Kepler's law and Newtonian gravity. Well, then you modify the gravitational equations to be general relativity, and you get what's called post-Keplerian or post-Newtonian methods, where you basically build in corrections that scale in powers of the velocity over the speed of light. But you assume point particles for that. And that works at low speeds. So it's a slow speed expansion, weak gravity, slow speed expansion. When you get to high speeds, close to the merger, then we actually use numerical relativity models, at least to tune sort of phenomenological waveform models that try and interpolate between the post-Newtonian theoretical models and the and basically computer simulations of binary black hole systems with full GR.
We have more questions. A question from William Black. These frequency versus time graphs look like they have a sort of honeycomb looking background. What's that from, and why isn't simply uniform?
You mean these things? Yeah. So there's let me see if I can find a better one. I'm going to go back to the first one I showed. And that's not a good one either. Yeah, so it's a bit of an issue of contrast and a bit of an issue of the wavelet basis that was used to construct these. So these are not like short Fourier transforms or something like that. They're actually constructed with wavelets. So the individual pixels sort of have a funny shape, and then there's a degree of contrast just to how it appears on the system. If I were to change the contrast so this was much less bright, then you would see the whole thing would be speckled, and it's just noise fluctuations that's causing that speckling.
So a question from Mateus Fabri. How do you differ between neutron stars and black holes from the data?
Oh, all right. Yeah. So the principal way, the one thing that we measure very well, see if I can find this. The thing that we can measure very well, and I'm going to go to the binary neutron star signal that I had, is the rate at which it increases in frequency. And that's determined by a particular combination of the masses of the two bodies called the chirp mass. But you can kind of think of it similar as the total mass. It's not quite the total mass, but it's a different combination. And higher chirp mass things will sweep up in frequency much faster than the lower chirp mass systems. So basically, the higher mass things, the gravity is stronger. They'll get pulled together faster with time. So this binary neutron star, you can see the axis here is measured in seconds. And in fact, this signal lasted for many tens of seconds in band. Whereas the binary black holes, if I were to go back up to one of those, they last for a fraction of a second.
So last question from YouTube. Could you could you give a short explanation of what kind of technology made it possible to have a 10 to the minus 21 sensitivity?
Okay, yeah. So there are many factors. One, you need a very long arm. So that's a bunch of technology, because you want the delta L over L to be, you want the, if you've got a certain delta L over L, you want L to be big to make a delta L. Then the point is that you can measure, you'd think that you could measure the delta L to within a fraction of a wavelength. So you would think that your sensitivity would be limited by a fraction of a wavelength over 4 kilometers. But that's nowhere near good enough. These are 1 micron lasers, so that's nowhere near good enough. So what you actually need to do is you need to, you're measuring not just one whole wavelength of change in your optical fringe. You're measuring as small amount as you can notice a difference. And that's related to the square root of the number of photons that you receive in a certain amount of time. So what you also need is a very high power laser. And our lasers aren't actually that high power, but what we do is we create optical cavities, Fabry-Perot cavities, where the laser is reflected back and forth within the arm many thousands of times to build up power. And that just creates that reduces the shot noise statistics and allows you to measure smaller and smaller fractions of a wavelength. That was for initial LIGO. Since then, there have been other improvements in the interferometry, in the techniques of the interferometry. And in fact, at the moment, we're now using quantum non-demolition techniques to put in squeezed vacuum states to drive down shot noise from the system as well. So there's a fair amount of quantum optics that are going into these measurements now.
So I think I'll thank everyone who participated in this YouTube broadcast, and reminding graduate students registered to the physics discussions can ask their questions after the YouTube broadcast has ended. And I think I'm gonna end the broadcast right now.